So Lenz's law says that the direction of an induced EMF will always be the direction that opposes the change in magnetic flux that caused the EMF to be induced. In other words, Lenz's law says that the EMF that's induced is always directed so that it's trying to restore the previous equilibrium. The EMF is induced because there's been a change in the magnetic flux, and the induced EMF is trying to put things back the way they were by somehow directing a current that will, moving charge, induce a magnetic field that will cancel out the change in the magnetic flux that caused the whole thing in the first place. And now James Clerk Maxwell enters the picture, and as you will no doubt remember from the walls of the Science Centre, this is one of Maxwell's equations, del cross E equals minus dB by dt, and using something which is known as the Kelvin-Stokes theorem of calculus, we can turn this into what's called its integral form. So, integral form. And in the integral form, it looks like this. It's the closed loop integral of E dot dl is equal to negative integral dB by dt dot dA. So, next line, closed loop integral E dot dl equals, let's take that dt out of there because we're going to take the derivative of something we've integrated. Good grief and good gracious. B dot dA, and then we're going to end up with integral closed loop E dot dl equals, well, let's have a think. Integral of B dot dA, hang on, that's phi. That's that thing there is the magnetic flux. So negative d phi by dt. And if we integrate the left-hand side, we'll get E dot L for length equals minus d phi by dt. And of course, an electric field times a length, E equals V of d, that will be a potential difference, minus d phi by dt. So, if we do it with Maxwell as our starting point, we get the minus sign appearing naturally, rather than having to be figured out that it ought to be there because of observation and experiment, as Lenz did. So we've got Faraday, who sorted out the magnitude, Lenz, who sorted out the direction, and Maxwell, who showed us how the whole thing comes together. And this is the version that we would use for a changing magnetic field passing through a conductor. So now you should be asking yourself why I've written the names of John Clerk Maxwell, Albert Einstein and Richard Feynman, the first, second and certainly top 5 physicists, in the middle of a discourse on induction. And the answer is that John Clerk Maxwell, Albert Einstein and Richard Feynman have all commented in scientific papers on the oddity that we get the same result. In other words, Faraday's law, that the EMF, the induced voltage, is minus n d phi by dt, whether we have option 1, a moving conductor, through a magnetic field, or option 2, a varying magnetic field, usually time varying, passing through a conductor. Now the reason this is odd is that we have to start from 2 different places in order to get to the result for each of these scenarios. But we get the same result even though we start from different places. In this one, a moving conductor through a magnetic field, Faraday considered a charged particle moving through a magnetic field. So essentially a conductor, a wire carrying a current moving through a magnetic field. But in this one, we were considering a magnetic field moving through a conductor. Now, so why is it that this particular oddity is so important? Well, it's because, while Einstein was getting his head around the 2 different routes to the same result, it made him think that there was no such thing as an absolute zero of motion. In other words, everything was relative to something else. No absolute zero point of motion. In other words, there was nothing that you could point at that was absolutely and unarguably stationary in relation to every other thing in the universe. So it's all relative. To something. In other words, whilst Einstein was thinking about electromagnetism and working it out, getting comfortable in his head how it was that you got, depending on a moving conductor through a stationary magnetic field or a changing magnetic field passing through a conductor, you would, by different routes, end up with the same result. That was what made Einstein think everything was relative to something else in terms of motion, and that, of course, is what led him to first special and then general relativity. Okay, so what can we actually do with this inductance idea in terms of solving problems and answering questions in exams? Well, let's start off with EMF equals minus n d phi by dt. Because we're going to need a definition of what inductance is, and conveniently it's defined using the EMF, and it's said that the inductance of a coil is equal to this here. So there's the EMF, which will be in volts as usual. There's the self-inductance, just the inductance for short, of a coil. Could be anything, but it's usually a coil. And there, of course, is the rate of change of current, which is in amps per second. And of course, an amp is a coulomb per second, so very rarely you'll see it as coulombs per second squared. Accelerating charges, good grief and good gracious, coulombs per second squared. And the logical consequence of this being Faraday's law, or Lenz's law as some reference books will say once you put the minus sign in, and this being our definition for inductance, gives us that the inductance of a coil is equal to n phi over double check how that works out. If we want L on the left hand side, then we're going to have EMF over di by dt on the right hand side. And if the EMF is minus n d phi by dt, then we're going to get L equals minus n d phi by dt over di by dt. And whatever you do, don't get your phi's and your i's mixed up here. So that's going to give us L equals minus n d phi by di. And if we just simplify it into the baby steps, that gives us our n d phi, n phi over I. But wait, you say, how did we get rid of the minus sign? We went from there to there, and a minus sign vanished. There's no minus sign there, there's no minus sign there, there's a minus sign there. How did we get rid of the minus sign? Well, that's quite simple. We forgot to put it in there, which means we'd have one there, and then two negatives, make a positive, and thus the minus sign is gone. Now, this is not, it has to be said, this is not the most useful formula in the world, because, you know, we're going to have difficulty measuring magnetic flux directly. Rate of change of current we can measure directly, usually from a graph. Yes, there will be graph questions. So let's look at, for example, the inductance of a coil as a special case, as a specific example. Well, let's see. We know that the magnetic induction in a coil, something with solenoid, is mu naught Ni over L. Now, yes, L for inductance, L for length. Yes, I know. And we know that phi, the magnetic flux, is Ba. So that's mu naught Nia over L. And we know that L, big L, the inductance is N phi over I. So N phi over I. Well, if that's what phi is, then that gives us mu naught N squared I A over I little l for length. So let's tidy this up. We've got L equals mu naught N squared. The two i's will cancel each other out. And an area over a length is just another length. But these are things that are easy to measure about coils of wire, so let's leave them there instead of trying to simplify the units any further. So, self-inductance of coil, inductance for short, mu naught, 4 pi times 10 to the minus 7, n squared, number of turns on coil, squared, little l for length of coil, and A for cross-section area of coil. Just like that. So, that's one you want to remember, and that's one you want to remember, and this is one you want to remember. This one, not so much.